we're now at the point where we have taken our video. We had a video, 8 gigabytes, plovdiv, and it basically had a bunch of Saber and I think it was Epe. We looked at the lights, broke them all up into clips, and we saved that data here where it tells us the frame of the starting action, the final action. So I've then taken it, I removed all the Epe, and I also analyzed each individual clip. So I also made a video of each of the Saber clips. I don't know how many I got, maybe a few hundred. And each one basically represents an action. And I then, each of these, so it's basically a video for each one of these rows. How many rows do I got? I don't know, maybe a few hundred? Yeah, about 300. Which makes sense, about half of them are Epe, half of them are probably Saber. And then this shows the frame with respect to the starting frame of when the light goes on, the red light or the green light. So you can see some of them have one, some have the other. Some of them probably have both, I imagine. Yep, a lot of them have both. So you get 2 lights on. And that's the frame. So it also has the call from the referee. And the way this call is based is I looked at the numbers, the score, and a lot of them, yeah, those look shaky. Are going to be, it's based on the score, based on which one is how the score increments. So if the left score increments, we assume it was left touch. All right, and a lot of this is broad strokes. I'm gonna have to go through all these and be like, oh, okay, this is not what we're looking for. And some of it's gonna cut up, not a big deal, broad strokes. All right, so now what we're gonna do is we're going to try to use computer vision to pick out data points. So the data points we're gonna look for are going to be the bell guard, the torso, the feet, and the score box. Partly because I think those are the important items, partly because that's what I already have annotated images of. So cut the story, long story short, I'm going to use, there's lots of different ways to do computer vision, lots to do different computer vision with tracking, detection, using Google Colab. What I'm going to use is referred to as, is going to be from Ultralytics and RoboFlow. Ultralytics does YOLO V8, which is not actually associated with the team that does YOLO V3 and YOLO V4. It's kind of like a spin-off, but their spin-off seems okay, good enough, and some interesting stuff. So RoboFlow is basically a platform to basically have data sets. So YOLO, you only look once, is object detection. That's what we're going to use it for. It can also do segmentation, it basically means it draws an outline, and it can also do classification. It basically says, here's an object, and this is what the object is. So, but we're only concerned with detection, specifically detecting the bell guard, feet, torso, and score box. So this is a blog post to basically talk to how you can go through it. YouTube video does a really nice job walking through it. And then they also give you a Colab notebook, which I'm basically going to use the same idea from. Copy paste most of it over. So the big thing is you're going to need a data set. I already have a data set, which is why I'm going to use it. I have a link to below. You can use my data set. It's got I don't know how many images. Many? Probably a few thousand. So we have a data set here. Looks like it has 829 images. And basically you can upload your images and you can see I went through and individually annotated. I used a different program. You can use RoboFlow to annotate. Lots of different programs you can use to annotate. It's not a big deal as much as it is tedious. You basically draw a box, be like, oh, that's the torso, that's a foot, that's a bell guard, that's a score box. And then you do this for a whole bunch of images. Now, one of the nice things about RoboFlow is that it basically lets you, what it can do is it can also alter the images slightly. It can change the basically the angle, the basically just muddy up the image a bit, and that way it adds variety when you're training the data. Okay, we got this so far. Let's go to the code. Pretty straightforward. So detection and tracking, make sure your runtime is GPU, because you're going to need a graphics processing unit to analyze this. I think it's graphics processing. I see graphics card. Oh, and you just look at the graphics card. It's like, oh, okay. Yep. We're going to install the library from Ultralytics. Yep, and I think that's just setting some baseline stuff. Not a big deal. Download what it has. And then we are going to take we're going to basically install RoboFlow, and this is where we're going to import our data from RoboFlow. So go back over to RoboFlow. So you go over here. This is our data. Click versions, I think versions. And you can't see it because it's behind my camera, but up here it says export dataset. Click export dataset. You can either download the dataset, which is what I'll link to, is just the dataset, or you can show download code. So what this does is this allows you to access the data straight from the RoboFlow website. If I was doing some sort of professional production type thing, I would not feel comfortable about relying on RoboFlow to store all my data, but this is just proof of concept. I'm just an amateur trying to show what can be done. Nice, excellent. All right, so now we have those downloaded. This is just a repeat of above, so I'm gonna get rid of that. So now we're gonna train the model. So mode, train, and we're gonna start by using the default weights. Yep, let's just go for this, see what happens. See how long it takes. Probably take a while. I don't know, maybe half an hour, maybe an hour, maybe a couple hours. We'll see. We'll just let it go, do its thing, and come back when it's done. So now that we've finished training our data, so we trained our data using YOLO V8 with which is by Ultralytics, and used RoboFlow to import the data set. We had to label everything, and our data set was something like labeled images using bellguards, torsos, feet, and I think score boxes. And so we did, after we did that, didn't take too long, trained for like an hour or so. We got a custom weight set, which we then saved. So this was, we saved in our Google Drive, best.pt for our custom weights. All right, so now that we have our data set trained, we're gonna track it. Now there is native tracking that we can do using YOLO V8, but it doesn't work as well. And the reason it doesn't work as well because it doesn't know what we're tracking. The way they're tracking things is just the generic tracking doesn't take into account the limitations of the fencer. And so it's worth our time to kind of go through and do this manually. Even if we don't do as good a job with the mechanics and coding of the tracking, the nuances that we'll be able to put from a fencing perspective will compensate for that. And so you'll see what I mean. So what we did, this is just downloads a lot of the dependencies, model weights, the video path, where our video files are that we saved, the clips of the videos. And that's just the clips of the individual fencing. And we basically filtered those out to pretty much just saber touches. We looked at the time. If the time says 3 minutes the whole time, it's probably saber. We look at points scored. If there is a point scored, it's probably also saber. That kind of means we're going to miss a lot of the simultaneous calls in saber, but there's not a lot of those anyway, and we might be able to work around that. So then, once we download all the dependencies, what I had the program do was basically go through each and every video file. So each video file in video files, where video files is the directory, output videos, and it basically does looks at the name to kind of analyze each video, but don't analyze a video twice. And it runs what I titled Run Inference. Run Inference is just a title that I named, and it's this function right here. So this function, it looks at the model. The model we used YOLO with our custom weights. Model weights are the custom weights we just did. Grab some data about the video file, basically the height and width. In this case, I think it's like 1920 by 1080 frames per second, which is about 30. And then it goes through and creates what I call a fencer list and a certainty list. So what it's going to do is for each, so I defined a class called fencer, and I don't think I get down to it right down here, left fencer, right fencer. So this goes, while true, read the video files. It basically says, look at the next frame in the video, and if you don't have a next frame in the video, then stop. That's basically what while true is saying there. So results here says, use the model and perform this inference. This is a part of the YOLO V8 library. It says frame, which is the frame, a video frame. Confidence just means anything is over 50% confident. Yeah, just use that as a detection. But pretty much if it detects it, it detects it. If it doesn't, it doesn't. There's not usually a lot in between. Persist equals true. That just means that I like to do the native tracking. It's mediocre, but it's fine. And then verbose, false just means don't add too much extra words. So then what the results put out is have boxes, classes, and confidence. So boxes is just the bounding box for a detection. This is for each detection. Gives us the bounding box. Class is going to be either torso, bell guard, score box, or feet. And then confidence. Confidence is how confident is each detection. And then what I do is I define a fencer class, a left fencer and right fencer, and come to scroll down here, see where I define fencer. So this class just has the properties of torso, basically the X and Y center, like the middle of the torso, the height of the torso, the width of the torso, the bell guard, X and Y position, and then torso frame, bell frame. What I do that for is it just helps me with a running average. Don't worry too much about that. It just makes life easier. All right, so then we come back up here to where we were. We created the fencers. There we go, right up here, left fencer, right fencer, and that's for each frame. So each frame, we're going to assume that there's a left fencer and a right fencer. And then it does frame count, initialize for initialization frames, which I think I said was 5. So basically for the first 5 frames, what we're going to do is we're going to look at the left, right fencers, and I'm going to do a function I call create fencers. What I do for that is it basically goes through and starts by looking at class number 3. Class number 3 is just the torso. When it says, hey, if you see a torso, and this right here, this just is the torso height. So if the torso is really small, don't look at it, don't worry about it. And this is basically like 1/10 of a screen. That is kind of a random pixel height that seems to work. So if the torso is less than 1/10 of the height of your frame, then it's probably someone in the background and it's not the person in the foreground. There's better ways of doing this. This is just kind of an easy, quick way of doing it, which seems reasonable enough. This basically says if the person is on the left side of the screen, he's going to be the left fencer. Person's not on the left side of the screen, so you get the else statement, else if. No, if else. The else statement right here, that basically if he's not on the left side of the screen, he's on the right side of the screen, so he'll be the right fencer. And all this right here, it looks complicated, it's not bad. It's just the way we do kind of a running average. So basically, I'm going to take the first 5 detections and average them. This looks complicated because if for some reason there's like only 4 detections, it basically takes into account that there's only 4 detections and therefore it averages using 4 instead of 5. It's not meant to be complicated. It just looks that way. Then we have an else if statement. This is if we don't have class 3, which is the torso, we instead have class 0, which is the bell guard, then it does the same thing, but for bell guards. And it does this for the first 5 frames. And the nice thing that gives, then we return left fencer, right fencer, which is just a class with all that data. This gives us the height and width of the fencer's torso, which is kind of nice because what I use that for then is for how far away the bell guard should be. So like, and I can't remember exactly what I used, but something like, you know, if the bell guard is 6 torso heights away, it's probably not the person's bell guard because their arm is just not long enough to do that. And that's what we're kind of going for there. So that initializes the fencers. And run inference. And then, so that's the first 5 frames. If you're not part of the first 5 frames, then instead do track fencers. So this is going to return us the left fencer, the left certainty, and the frame. Basically, the frame is the image. I pass the image in. That way, if I want to do any like drawing on the image, I can draw on it and track fencers and bring it back. I probably didn't need it. I did it anyway. So track fencers, just another function. Track fencers have all this data we put in, left and right fencer, and we also have previous fencer and the previous fencer. So I'm looking not just at the data from this fencer, the fencer in this frame, but the fencer in the previous frame and the previous one before that. And what we do is I basically find out how fast the bell guard is moving. So we start with, I say bell guard here, but this is actually for the torso. So we find out how fast the torso is moving. We find out where the torso is, or previously torso was. And then we're like, all right, if the torso was here, we know it's moving this fast, we expect it to be there. This is just some very primitive way of doing some tracking. Another nautical concept that's similar would be dead reckoning. And so we do this, we find a box, we look in this box, we're like, all right, we expect to find it in this area, this region, and we look through all the detections, like, all right, if you find a torso in this region, we're expecting the torso, then that's the torso. And that's the idea here. We find the torso first because the torso is easier and more reliable to find than the bell guard. And we found the bell guard second because now we can use the position of the torso to limit where we expect to find the bell guard. And I kind of do that in here. Basically the X2 position, so X1 is on the left side, X2, if you have a screen, X1 is the minimum, X2 is the maximum. And so that's why the left side, the minimum is going to be basically X1 is going to be close to the fencer, X2 is going to be away from the fencer. And I do something here with previous certainty, basically that if you didn't find the detection last time, make your box a little bit bigger for your searching. So as you're uncertain, the box gets a little bit bigger. Nothing too nuanced there. So for here then, this is basically, when we initialize the fencer class, it sets everything to 0. So if the bell guard position is 0, that means that we weren't able to find it through a detection. So what I do then is I use the expected value. So this is expected value. So we knew where it was twice before. We knew where it was before. We should be able to then kind of draw a line through those and be like, oh, here's where it should be. And if we didn't find any detections, that's what we go for. And then there's just kind of some nuance in how to do that. And then that's the basic entire thing of the tracking. Not overly complicated. Actually very simple and primitive. So then go back to our inference. Is this what we're looking for? I think so. Yep, run inference. So this is the track fencers. And then, so now we have pretty much all the data we need. So the idea is I draw some boxes on it to make it look pretty. So for this linear interpolation, what I'm doing is I'm passing in the fencer list, which is just each fencer class, which has position and other variables associated with each fencer and each fencing frame, and it has a list of those, one for each frame of the video. And also I have an uncertainty list. So what I do in this, so let's say uncertainty, where 0 is certain. Oh, terrible handwriting. I apologize. 1, not certain. So we have some video frames with like 0, 0, 1, 1, 0. This might be like 1, 3, 12, 2. Let's see here. 9? I'll try 9. And so we have these are positions, and I'm concerned with the X position of the bell guard. So X position of the bell guard. So if we know where and this is the certainty, and these kind of correlate to each other. So it's like, all right, we know that 1 is good because it's certain. 3 is good, that's certain, and 9, but we don't know about these two. And so what it does is, if you have a detection at 3 and 9, what it does is like, all right, let's look at the difference between these two. 9 minus 3 is 6. 6 divided by 3, because we're looking at 3 values, is 2. And so it's like, all right, we can plug in then 3 plus 2, which is 5. 5 plus 2, which is 7. So what it does is it would adjust this to 1, 3, 5, 7, 9. So it basically smooths out the values when it's uncertain. Now, there's a big risk to that because you're going to have a lot of uncertainty when the picture is blurry. Picture's going to be blurry when people are moving fast. When people are moving fast, this pattern of smoothness is least likely to hold. So the points where you want the best data, we're just kind of assuming the best. And it's like, maybe. Less than ideal. And that's basically all that's going on here. You can look down here at the code. That's just what this code does. So not too big a deal. I'm gonna take a look at a tracked image real quick. So let's see here. Yep, these are some of the tracked videos we have that I put out. So tracked videos. We'll just grab one pseudo-randomly. How about this one? Download. We'll take a look at it, and you might be able to see what we're doing. So opening up this video, 495,900. Up, bring it over here. So this is what the video looks like. So let's slow it down so we can actually kind of see what's going on. So they can start fencing. So you can see here, it wasn't even picking up the bell guard. No idea why, but then it does, which is nice. And so as they're going forward, you can see on the right fencer here, they had the bell guard, but it lost it. And so then it comes forward. Man, that's a lot of missed frames there. And I think it actually grabbed the opponent's bell guard right there. But it tracked it all the way through. That is terrible. Let's look at the left fencer instead. So detection, ID 12, right here. Misses it, and then it picks it up again. And so what it does in those in-between points is it basically just averages them. And it worked out pretty well. And it just does the X position, so that's why you see the Y position kind of drifts off, and it snaps into place. But it's that after looking at the values afterwards, that kind of makes it close. And the green position for the hand is surprisingly plausible. So it's like, yeah, maybe. And they come together. So, ideal? No, not ideal. But considering what we're working with, not as bad as it could be. And then this one will be pretty easy because it's one line. All right, so that's kind of what we're talking about with the tracking and how the linear interpolation goes. I think interpolation, is that the phrase I used? Probably. So, yes, here's linear interpolation. Then we draw some pictures, draw dots on the bell guards and the torsos. This just builds the list for the fencer class and then the certainty files. The certainty just ones and zeros of how confident it is in each detection. Then it releases the video. So then this section here, we're trying to find the maximum frame where the green or red light turns on, because we don't need to go anything past that. Yeah. So then we have the velocity. The velocity is just going to be the difference in position from one frame to the next. So we do the velocity minus previous velocity divided by the frame, which is just 1 in this case. Long story short, difference in position with respect to time, in this case frames, which is synonymous because 30 frames per second, gives you velocity. Difference in velocity with respect to time gives you acceleration. That's what I'm measuring here. And I'm just storing it into a CSV file, comma separated values, basically a fancy Excel spreadsheet. Good for data analysis because it's simple. And then I'm normalizing it to between -1 and 1, because that just makes data easier to analyze when things are between -1 and 1. And that's basically all that does. So to give you an idea here, each of these video files, the clips that we analyze, has a what I call acceleration output. So you have your left fencer, right fencer, here's the acceleration, and here's the red light, green light, and when it turns on. So what you can see here is this is the acceleration of the left fencer. So going forward, going backwards, yep, and right, going forward, going backwards, and then you see the left light turns on at frame 41, and the green light turns on at frame 46. So the idea is this is going to be the data that explains that clip by measuring the acceleration and when the light turns on. So we save all that, and once we have that all saved, that now is what we're going to use, all these acceleration files, what we're going to use to feed into an AI model, which we'll figure out next time. And that will kind of give it, hopefully, we'll see, maybe, we'll be able to use to predict whose touch is which. So the data that we'll use, so we're going to take those acceleration files, we'll put them in, and we're going to use clips.csv, correlate it based on the middle frame, and we know which touch is correct, right or left, based on this column right here, which we found using basically the increment in the scoring. So that is what we did. That's what we have. One of the cool things we were able to get here was a whole bunch of videos, tracked clips. Now I have all these cool clips that we can use. Just look at a random clip right here. See how it looks. And you see the clip following the hands. And that one's kind of not as good because this works better head on. With a march, it's going to be a little bit not as nice. Hope, there we go. Hope, track, and go. So, hope that helped. See you next time when we actually try and analyze the data we had to make predictions. Take care.